For reasons that we've already been over, linear approximations to functions is a good way to approximate the function, at least locally. So let's remind ourselves of what this says. A function may be approximated by another function, a linear function, where the linear function is we have a y-intercept, so to speak, so an initial value given to us by the function. So our function evaluated at some point plus the derivative of the function at the point, so the slope of the tangent line there, and then we travel along the tangent line. So the derivative times the change in the distance should give you, this term kind of gives you a dy or a change in y. So you have your initial point, and then you add your change in your y, that should give you your line, your new y value. And it's a decent approximation for the actual function as long as this distance is not too large. All right, so I'm going to leave that alone, and let's apply this to our problem here. All right, we want to find a linearization for this function, f of x, which is square root of 1 plus x. And we want to establish this linearization so the x naught, the point that we're interested in, is going to be 0. So our function can be approximated by a linear function. In fact, I'm just going to write down exactly that same thing. So let's go ahead and apply it to our problem. What is our function at our value of interest? X is equal to 0. So if we plug x is equal to 0 here, we get a 1 plus 0 is a 1, square root 1 is a 1. Oops. Now the derivative at 0, first we need to find the derivative of our function. So our function can be rewritten as 1 plus x to the 1/2 power. So it will differentiate to 1/2 times 1 plus x to the minus 1/2 power, and then times a 1 by the chain rule. So simplifying this gives us a 1 over 2 root of 1 plus x. And if we evaluate our derivative at 0, because that's what we want to do, the derivative at the point of interest at 0 is going to be a 1 over a 2. And then we will multiply that by x minus x naught. So we want to leave this alone because that's going to tell us how far we need to travel. Right? Like if you're solving an equation for a straight line, you want there to be x's there. Oh, sorry, but we do know x naught. The point of interest was 0. So let's make a final sentence. F of x can be approximated with a linear function by having an initial value of 1 plus m times x, right? Slope times x. So 1/2 times x. All right, now we want to use this linearization to approximate the function value at 0.1. So f at 0.1 is approximately the linear function at 0.1, which is 1 plus 1/2 times 0.1 is 1 over 10. I like fractions. This is 1 plus 1 over 20, or 21 over 20. Okay, now we can actually find the value of the function at 0.1 by just plugging it in. Our function at 0.1 is going to be the square root of 1 plus 0.1, or 1 over 10. That's the square root of 11 over 10. All right. So if you wanted to, you can find the error in your, oh, that's actually coming up. Hold on, I don't want to get ahead of myself. Our next job is to sketch the function of the tangent line on the graph provided. So let's clear off some work here. Right, the only important part is this tangent line that we give ourselves and this approximation. So let's clear off the board. Now let's graph the original function f of x, which is the square root of 1 plus x. So that's going to have an x-intercept at -1. And it's going to look something like this. Now, when x is equal to 0, our tangent line, let's zoom in there, looks something like this. In fact, that line is given to us by this right here, 1 plus 1/2 x, right? It has a y-intercept of 1 and a slope of 1/2. That's the value of my derivative. And we said that the value of our tangent line here at 0.1 was, what did we say? 21 over 20. And the actual value of the function was square root 11 over 10. Okay, now we can ask, what is the error in the approximation? So the error in the approximation is defined as the difference of our function and the linear approximation, right, in absolute value. So if you do this, I'll skip the algebra. We can certainly subtract two different values and find the absolute value of it. The difference in the linear approximation and the actual function value is 0.00119. So it's a pretty decent approximation. All right, last step. Let's repeat the process to estimate f of 2 and find the error. So here I'm going to go a little bit quicker. I want to leave my tangent line alone. And I want to approximate the function value at 2, which is approximately the linear function, the straight line at 2, which is 1 plus 1/2 times 2, or a 2. All right, so our straight line over here at 2 returns us a y value of 2. The original function returns a y value of square root 3. Now the error in that approximation is the absolute value of the difference. So that is the absolute value of square root 3 minus 2. And again, skipping the algebra, you end up at 0.2679. So notice your error got bigger because you tried to move too far away.